Alright, welcome to another AQA A-level chemistry video. This is a continuation from the part 1 video on the equilibrium constant. This part 2 video will be me going through exam questions on the properties of Kp. After that, the first thing I'm gonna do is go through this exam question on how to actually calculate Kp, which is very easy to do. It's 7 marks, 7 easy marks. Once you see me do it, you realize how easy it is to do. It's kind of similar to calculating Kc, but obviously it's more tailored to actually answering Kp. There's some adjustments to make. But after this, on me answering that question, I'll let you guys answer some exam style questions I've put down, and then I will go through it and then go through the mark scheme of it. If you just want to go straight to the question and look at the whole question paper and the mark scheme, I've left a link in the description to that. I have to link in the description to the question paper and the mark scheme if you just want to go straight to that. Anyway, enough of me waffling. I'm going to go try and answer this question now. So this is a 7-mark question, how to actually calculate Kp. Now I will try to do this in 7 minutes because I usually like to do a mark per minute, but I'm explaining this as I go, so I might not make the 7-minute timer because I'm trying to explain to you guys as I'm going through. But I'll put the 7-minute timer on, just show that, because technically, realistically, answering questions like this, once you get the hang of them, you should be trying to answer this question in 5 minutes, and that saves you a bit of time at the end of the exam to kind of look through. But yeah, I'm gonna try and answer this question. I might not get the 7 minutes timer on the dot, like I have with other sections, but yeah, I'm gonna be making sure that I try to explain as much as possible. So if you see me not make the 7-minute timer, just know that it's not because I can't make it, it's because I'm trying to explain to you guys as I go through it. I'll set the timer on my watch as well, but I'm gonna leave the timer here as well. So yeah, I'm gonna try to do this now. Okay, so a chemist investigates the equilibrium shown below, which is that equation there. A chemist mixes together 1 mole of CH4, 1.4 moles of H2O in a sealed container. The mixture is heated to a constant temperature and allowed to reach the equilibrium. The equilibrium mixture was found to contain 0.2 moles of CH4 and the total pressure is 30 atmospheres. Calculate Kp, 7 marks. Okay, so the first thing I do in a question like this is I would first of all, I write down the equation. So the equation was what again? CH4 plus H2O gas goes to form 3 moles of H2 plus carbon monoxide. Okay, so the first thing I do is write the equation. That's part 1. Part 1, CH4 plus H2O. So this part is similar to how you would answer Kc. And the reason why I put down the equation, you don't get any marks for this, but it just allows you to make a comparison so that when you do the actual mark now, which is doing the ice table. So now it's this again, you don't get marks for doing the table, but it allows you to help you answer this question. So the initial moles of CH4 was 1, so 1 moles of CH4, 1.4 moles of H2O. This is the initial moles. The initial moles were forming H2 and carbon monoxide as a product, so it's going to have the initial moles are going to be 0, and then when it in equilibrium, 0.24 of CH4. So okay, so that's 0.2 moles here. So then we have minus 0.8. Yeah, minus 0.8 here as well, because we're taking away 0.8. Because they're both from 1 mole of each compound. That's 0.6. We're forming the product, so we're gaining moles here. So that's plus 0.8 moles of carbon monoxide, but it would be technically you have 3 moles of H2, so it's plus 3 by 0.8, which is 2.4 moles. Now we go for the part we have now the equilibrium moles. Now here, part 3 is working the total, getting the sum of all the moles, sum of the equilibrium moles, which is 0.2 plus 0.6 plus 2.4 plus 0.8. That is equal to 4 moles in total. Part 4 of this is working out the mole fraction. I already explained why we work out the mole fraction and why it's important to work out the mole fraction, what it represents in the part 1. I told you what the mole fraction is all in the part 1 of this video. So mole fraction would just be the individual equilibrium moles over the total number of moles. H2O, H2, carbon monoxide. Right, so CH4, 0.2 over 2 over 0.2 over 4, that's 0.05 moles. 0.6 over 4, 2.4 over 4. Hopefully you can see where I'm getting along with this. The mole fraction is just literally the number, your equilibrium moles, individual equilibrium moles over the total moles. I can see it that everything I've done right now, it all lines up. I can see that 0.2 is for CH4 because I wrote the equation at the start. It doesn't, you don't need to do that, but it's kind of something that can be useful for you when answering questions. Makes it a bit more clear. It makes your answers more clear. If your answers are more clear, it's easier for the examiner to see what you were trying to write down, and it makes it easier for them to give the marks to you. 0.15. I can tell that's 0.6 from here, and then this would be 0.2. If I'm not mistaken. Right, cool. The next part now I'll try and put this here. Try and make it more cleaner than this. Obviously, they'll give you a bit more time, more space to do it in the exam. And even if you are going to do it, don't make it a little curl like that. I'm just doing this to separate them out. The step 5 for this now is now working out our partial pressure. Partial pressure is equal to the mole fraction multiplied by the total pressure. And they've given us the total pressure, which is 30 atmospheres. So the the partial pressure of, remember we represent partial pressure by this, brackets and P, CH4, partial pressure of H2O, partial pressure of H2, and partial pressure of carbon monoxide. .05. So our mole fraction, our partial pressure is the mole fraction times by the total pressure. So mole fraction of CH4 is 0.05 times by the total pressure, which is 30 atmospheres, 0.15. Oh, wait. It'd be 1.5, sorry. Mental maths is... See, don't be cocky like me. Use a calculator. There's nothing wrong, you know. In A-level chemistry, you're allowed to use a calculator. Don't be daft like me and try to think you're so smart by doing it. Just be simple. And yeah, you'll be fine with that. So 0.15 multiplied by 30, 0.6 times by 30. How much time have I got left? 1 minute, 4 seconds, 3 seconds. 0.2 multiplied by 30. 0. Let's not try and be smart. 0.15 multiplied by 30. 4.5 atmospheres. Again, I'm probably not going to finish this question in time, but as I said, I can do this question in time. I'm just trying to explain to you every single point so you can understand what I'm going through. 18, and then 0.2 times by 30. Scared the crap out of me. 6 atmospheres. Right. Then that's the part. That was part 5 of that question. Part 6 is writing out our equation. Writing out our equation for this, which is writing out the equilibrium equation for this, which is, so Kp. We now have our partial pressures. Now we need to sub in our values to work out our partial, to work out our First, we need to write out what the KP equation would be for this, which remember is always your reactant, your products over your reactants. And then once we've have that, we can then we can substitute our values in and then work out the KP. So most people would put this at the very start, and I usually would. I don't know why I didn't put it at the start, but yeah, I'd advise writing your equation at the start, because it's usually one of the marks they like to give at the start. But as long as they can see it, that's fine. It's just that I could see doing all of this very quickly. That's why I did that. But this is always a mark. Writing out this is always a mark. So pH2 cubed. Remember how I explained it before? It's your partial pressure of your compound, or partial pressure of your whatever you have of one of your products, and then your power is your your molar ratio. So here there's 3 moles of H2, so it'd be H2 cubed times by P carbon monoxide all over P CH4 times by P H2O. And then part 7 of this question is just literally, part 7 now is actually substituting your values in. So H2 was what, 18 atmospheres. So 18 cubed by 6 all over 1.5 times by 4.5. 1.5 times by 4.5. Oh, 18 cubed by 6 over 1.5 by 4.5. And that is 5,184 atmospheres. But you're not done, because like how when we're doing the rate constants, you have to work out what the units are, and same thing with Kc, you have to work out what the units are. It's the same thing with atmospheres. Now we're using atmospheres here. Now I can see from here it's atmospheres squared. How I know that? Literally, it's what you have is from here, right? You use this is why your rate constant, your not rate constant, your equilibrium, your KP equation is so useful, because it allows you to work out your units as well. So it's atmospheres cubed. Now that's the answer, by the way. That's the answer, by the way. But you have atmospheres cubed. Why have I done it like that? Anyway, atmospheres cubed times by atmospheres all over atmospheres times by atmospheres, which is just atmospheres squared, really. But I just wanted to represent it like this because of how you see it. Cancel that one out, cancel that one out, cancel this one out, cancel this one out, squared, atmosphere squared. And that's it, right? That's it. And now I've made it look really long, but I could just redo this question now and do it. I mean, I've already done it, so I mean, technically I wouldn't be able to do it, and I'll be able to do it faster, obviously, but this doesn't take you long, right? It doesn't take you long. I've just explained every single point. It does not take, it may look long, but it's not long at all, right? It's just, that's what she said. Anyway, this here, really, you can do this whole thing here within 1 minute, 2 minutes, maybe, right? Definitely less than 2 minutes. This part here takes another minute, right? So that's what now, 3 minutes. 4 minutes into 1 minute, I guess, for writing up this, 1.5 minutes for that. So that's 4.5 minutes now. Have I done this right? 2, 3, and 4.5, and then 5.5. Ah, no. Sorry about that one. 5.5, getting that. And then really, once you get that, you can then work out this. Now, 5.5, and you could do that 6.5 minutes. Now, if you do it more often, you can just clearly see this, and you can probably do it close to 5 minutes. You knock a minute and a half off of that. And in this, really, you don't even spend any time doing that. It's like a couple seconds, really. And you don't have to actually do this, write this out. You can see that mentally. Right, so I'm going to make you guys look at a couple of exam questions I want you to do. And then after that, I'll answer them. So, yeah, look at them. So pause the video now and then try to answer them. Or pause them at the individual questions that you want to do and then try to answer them. Alright, so I forgot to mention that this is actually a 21 mark paper. So I haven't started yet. Spend 21 minutes on this. I'll say paper, but the amount of questions I have is 21 marks in total. So spend 21 minutes on this. And yeah, so I'm going to try and do this in 21 minutes. I'll try not to speak too much or emphasize on speaking too much. I'll try and speak as I go, but mostly I'll be just going, trying to answer the questions. And 21 minutes there. Okay, so manufacturing loss production shown below. The graph below shows some partial pressure changes with time at a constant temperature. Draw across an appropriate axis of the graph where the mixture reaches equilibrium. Okay, so draw across on appropriate axis. Well, the appropriate axis when you're reaching equilibrium should be time. What time does you reach equilibrium? And so time when it reaches equilibrium is x-axis, so it should be like there. Okay. A 0.230 sample of carbon monoxide is mixed with hydrogen in a 1:2 mole ratio and allowed to reach equilibrium in a sealed flask at temperature T. At equilibrium, the mixture contains 0.12 moles of carbon monoxide. The total pressure of this mixture is 1.04 times 10 to the power 4 kilopascals. Calculate the partial pressure in kilopascals of hydrogen in the equilibrium mixture. Okay, so I have to work out the so I'm calculating the okay. Partial pressure in kilopascals of well, partial pressure is equal to the mole fraction times by the total pressure. So in order to work out the partial pressure of hydrogen, I need to have the mole fraction. Actually, I need to do an ice table. So I'll write down the equation for this so I don't have to keep scrolling up and down. So carbon monoxide plus 2H2 goes to form CH3OH. 0.23. So the initial moles of carbon monoxide is 0.23. And hydrogen is also 1:2 mole ratio, it says here. So times that by 2. So 0.46. Sorry. Senor. And there's an initial mole of methanol is 0. The equilibrium moles of carbon monoxide is set. 0.12 moles of at equilibrium. So 0.12 moles here. That's minus 0.11. So plus 0.11 of, so we're gaining 0.11 moles of methanol in that case. Oh, sorry, there we go. And then we're losing 2 moles of hydrogen because it's times 2 TH2. So that's 0.22. So 0.46 minus 0.22, 0.24. Okay, and now in order to work out the mole fraction, we need to have the total number of moles. So total number of equilibrium moles is equal to 0.12 plus 0.24 plus 0.11, and that is equal to 0.12 plus 0.24 plus 0.12 12 plus 0.24 plus 0.11, 0.47. Go. Okay, then I said mole fraction is equal to partial pressure is the mole fraction as by total pressure. So the mole fraction of hydrogen of H2 is equal to 0.24, the individual equilibrium mole of hydrogen, over the total number of moles, and that is equal to 0.24 over 0.511. Well, it rounds to 0.511 anyway. Sorry, I just went blanked out there. Therefore, the partial pressure of H2 is equal to the mole fraction, which is 0.511, times by the total pressure, which is 1.04 times 10 to the power of 4. And that is equal to 5, or roughly rounds to 5,311 kilopascals. I'm going to come back to this because it says 3 significant figures, and I've given 4, but I'll come back to that one. I don't want to waste too much time. Kp, given expression for the equilibrium constant Kp for this reaction, state the units. So Kp would be equal to I'll have it here. Partial pressure of methanol over the partial pressure of carbon monoxide times by the partial pressure of H2 squared. And then the units would be, I can just see here, it's kilopascals to the power of -2. The reason why is you have cancel that one out, cancel that one out. You basically just have 1 over kPa squared, which is the same as kPa to the power of -2. Good. And then, so some more carbon monoxide is added to the mixture in part B. The new mixture is allowed to reach equilibrium at temperature T. State the effect of any on the partial pressure of methanol and on Kp. So effects of partial pressure. So we're adding more moles of carbon monoxide. Therefore, our mole fraction will be different. It'll be larger. We're still multiplying it by the same total pressure. So our mole fraction is higher, but our total pressure is staying the same. Therefore, the partial pressure should increase. The effect on Kp will have no effect on Kp because it doesn't affect the position of equilibrium on Kp, I say. State the effect, if any, on the addition of a catalyst on the effect on the value for Kp for this equilibrium. So explain your answer. So the effect for value of Kp is, well, I can easily tell it has no effect because catalysts don't affect the position of equilibrium. They don't cause shifting of the position of equilibrium. I'll say it doesn't affect the position of equilibrium. It's the same thing, right? Only increase the rate of reaction. Okay, so that's that. How much I spent? 9 minutes on that question. That's not too bad. sulfur trioxide decomposes on heating to form an equilibrium mixture containing sulfur dioxide and oxygen. A sample of sulfur trioxide was heated and allowed to reach equilibrium at a given temperature. The equilibrium mixture contained 6.08 grams of sulfur dioxide. Calculate the mass in grams of oxygen gas in the equilibrium mixture. Okay, so, this is just a simple mole calculation question. Yeah, easy. So moles of SO2 is equal to, so moles is equal to the mass over the mR. I don't know why there's a capital M there. So that would be 6.08 over, sulfur is 32.1, so, and oxygen is 16 but times by 2, 32, so that's 32.1 plus 32, that's 64.1. And that's equal to 0.94, so 9.49 times 10 to the power of minus 2. So 9.49 times 10 to the power of minus 2 moles. So 2 to 1 molar ratio. Therefore, moles of oxygen is equal to 9.49 times 10 to the power of minus 2 over 2. Therefore, the mass of oxygen is equal to whatever that is times by the mR of oxygen, which is 32. So that divided by 2, 4.74. 4.74 times 10 to the power of minus 2. And then 4.74 times 10 to the power of minus 2. And then times that by 32. .52, so that's equal to 1.52 grams. At different temperatures, a sulfur trioxide was heated and allowed to reach equilibrium at 1050 Kelvin. For this reaction at 1050 Kelvin, the amount of each substance in the equilibrium mixture is shown in the table. For this reaction at 1050 Kelvin, the equilibrium constant Kp is 7.62 times 10 to the power of 5 pascals. Okay, so then calculate the mole fraction each. Okay, so these are individual. Yeah, calculate the mole fraction each substance at equilibrium. Give the expression of it. Yeah, these are all individual questions, really. I like to put dots around them, boxes around them, so I can tick them off as I go off. So make sure I've answered every aspect of the question. So the mole fraction, SO3. So actually, these are all at equilibrium, so I can just add them all up. So I don't need to actually do too much calculation here. I can just do that. I've already done that for you. Plus 1 point, why have I done like that? 0.32 plus 1.2 plus 0.6. That's equal to 2.12. 2.12. And then just the individual mole fraction. So 0.32 over 2.12. Now, three significant figures in this question. So I'd say 0.151. Sorry, 1.2 over 2.12. 0.566. 0.566. And then 0.6 over 2.12. 0.283. It's just this over this. All right, done that first part. Calculate, given the expression for the equilibrium constant Kp. I'm going to do it here so I have more space to do it. I know it's kind of covered there, but giving myself more space here, and that's just give an expression for it. It's just partial pressure of SO2 squared times by the partial pressure of O2. It was always product over your reactant, so it's very easy things to do here. Partial pressure of SO3 squared. Done the second part of this now. Calculate total pressure in Pascal. The total pressure in pascals. Okay, so wait. Calculate the total pressure. Okay, so partial pressure is equal to the mole fraction times by the total pressure. And then I could just rearrange total pressure is equal to partial pressure over mole fraction. I think I encountered a question like this before when I was doing A-levels at the time. Okay, all right, so how I would, yes, yeah. Okay, so, yeah, okay, I know. So we know that Kp is equal to the partial pressure, this basically, right? The Kp is equal to this, right? This represents, for example, this here represents the partial pressure of SO2 squared, of SO2, right? So that can be represented, but we don't have the partial pressure of it. We have the mole fraction of SO2. That's what we have. We have the mole fraction of SO2, right? I have the mole fraction for every one of them. So what I would do is I'd represent that as in my equation. So Kp, I'm going to represent total pressure as X. So Kp is equal to SO2 squared times by X squared, because that's what really you're doing this, right? So I wasn't going to do too much explaining, but SO2 times by X squared, aka you can also write it as, to separate them out to make it easier for you to get, because we want to separate X out, right? Because we already have SO2 here, but I'm just doing it for the sake of showing you guys. So SO2 squared times by X squared, same thing as what I wrote before, times by O2, the mole fraction of oxygen, times by X, all over SO3 squared. How much time have I got left? 4 minutes and, okay, 4 minutes and 41 seconds. SO3, mole fraction of SO3 squared times by X squared, right? So now I can cancel out the X squared here, X squared there. So I just have X. If I want to work out X by itself, X is equal to Kp times by SO3 squared all over SO2 squared times by O2. And therefore, now I've done it now. That's it. I've just solved for X. Now I've got to substitute in my value. So they've already told me X. So they already told me Kp. Kp is equal to 7.62 times 10 to the power of 5. The SO3 is 0.151, and then we're gonna square that because that's what we're following this now. We've made a little equation for ourselves. All over SO2 squared, which was 0.566 squared, and then O2 is 0.283, and that should give us X, which is the total pressure. Hopefully that made sense. Hopefully I was speaking sense when I said that. So 7.62 times 10 to the power of 5 multiplied by 0.151 squared over 0.566 squared times by 0.283, and that should be, I'm going to round down to 3 significant figures, but 1.92 times 10 to the power of 1, 2, 3, 4, 5. So 1.92 times 10 to the power of 5. So 1.9. If I round it, so 1.92 times 10 to the power of 5 pascals. All right. 2 minutes actually I've got to do okay. For this reaction at 1050 Kelvin, the equilibrium constant Kp is 7.16. Explain how this information can be used to deduce the forward reaction in the thermic. Because as temperature increases, Kp increases. Suggesting that's a terrible way of saying suggesting equilibrium shifts to the right. Shifts to the right to favor the endothermic reaction. So I've got now 50 seconds left, okay? Use different velocity to calculate the value of Kp at 500 Kelvin for equilibrium represented in the right equation. This equation is half of... Yeah, it's essentially just half, so I just square root it. Because now it's just going to be... The power is now halved, so everything's just going to be... So square root of that is of 3.94 times 10 to the power 4. 198.5, and literally kilopascals to power of minus to power of a half. There, because it's just half, and I've got 7 seconds left to stop that. But yeah, that's it. I should have had more time. As I said before, I'm trying to speak as I'm going through this, so it won't be exactly in time. But yeah, that's it then. But the reason I just want to clear up why I'm in here. So here, this equation, as I have to rush towards the end to make sure it's done in time, but this equation here is half of, in terms of moles, of this equation. You see, the equation that we have below is just SO3 SO3 goes to make SO2 plus half O2, and that's half of this, which means it's going to have half the number of moles. Therefore, we have to our power is going to be half, and when you have when your power is a fraction, it usually represents some sort of root. So 1/2 is the same as square root. When you have a power of 1/2, it's the same as the square root. In maths anyway. Anyway, I'm kind of waffling now, and I'm just gonna go to the mark scheme to this. So let's just go and compare this with the mark scheme. What was its question? This question is question 2. So green pen now. Okay, so X is, that's correct. It should have been 5,310. So I've done everything else here, right, in terms of equilibrium is 0.24. And by the way, you don't have to say it specifically, as long as you show it in, like doing an ice table, they know how to do an ice table here. So they know that you know that this is 0.24. They'll see that and say that's M1. M2, working at the mole fraction, done that. So I will total number of moles 0.47, done that. It's just that last part now of just, this should be, I said I was going to come back to it here, but anyway, let's not make too much excuses for myself. That should just be a 5,300. It was originally 5,310.8, I think, or 0.5, so I'll round it up to 0.11 to 5,311, but it should be 5,310 because we're only doing it to three significant figures anyway, so leave it as that. So 3 out of 4. This now is KPA to power minus. Yeah, that's fine. Yes, that's fine. That's fine. That's fine. Increase. No effect. No effect. That's 0. That's 2 marks there. No effect. And then increase the rate of forward to backwards reaction by the same amount, or catalyst doesn't affect the position of equilibrium. Actually, word by word, so that's perfect. So either or is fine. That's 2 marks there. How much for out of 11 I got there? 10. Not bad. How much did I get out of this? 1.52. This is just simple 1.52 grams. I mean, what's the other one for working out 0.474? Yeah, just that. Or 0.0474, 4.74 times 10 to the power minus 2. That's fine. You get a mark for getting mixture. Oh, but why? Well, these are correct, but it's not to the same number of significant figures. But I'm trying to understand where it is that all of the questions here. I'm sorry, I'm a bit confused by this. They've done it here to 2 significant figures, but the answers, all the information that we have is all in 3 significant figures. I'm a bit confused why. What's wrong, but I don't know where I went wrong. Well, this is correct, but it's the significant figures that alter it. If a teacher's ever watching this, I hope please explain to me why. I thought it should be 3 significant figures, unless it's that I don't see where it says 2 significant. I mean, I don't see any values where it says 2 significant, where it shows 2 significant figures. I mean, well, that messed that up, I guess. The KP is correct, so that's no problem there. Will I end up giving myself a mark? Or I can't, because I haven't. That's technically not correct, so I can't give myself a mark there. Did I get this question though right? Yes, working out the pressure. I represent the pressure as X, but yes. Yes, yeah. I've seen it here, and this is correct. So this, if you do either of this or this, that's another mark. And then the answer will be anywhere between 1.88 times 10 to the power 5 or 1.94 times 10 to the power minus 5. And the mine is clearly right there. So that's a mark there. So 1, 2, 3. And I guess technically I can't give myself 4 because that's not the right number of significant figures, but I don't really know why. But I have to give myself 3 there. So as temperature the next one is KP is higher as temperature. So KP is high at high temperature, or as temperature increases, KP increases. I'll give myself a mark for that. That means the same thing. At high temperatures, more social occurs, more products. Equilibrium shifts to the right. I said that equilibrium shifts to the right to favor the endothermic reaction. Well, that's 2 marks. You'll get me out for that. And then the next one is 198.5. Okay, yes. No, it's meant to be in pascals, isn't it? I can't give myself a mark for that. That's for rushing. So yeah, but hopefully if you actually do these questions in real life, you will be doing them without me talking, as you'll have enough time. I make it sound like we don't have enough time. You'll have plenty of time. If you're doing at the pace that I was doing them in terms of like actually answering the questions quickly, you will be able to answer the questions with enough time at the end to look back over your answers, and you can spot some of simple things like this. This I don't know really about too much, but definitely things like this here. So yeah, overall we'll get like 19 out of 21. Not bad. Yeah, anyway, hopefully these two videos are helpful, and that's it. I'm done.